The 2025 Physics Nobel Prize has been awarded to macroscopic quantum tunneling. I don't know anyone who had this on their bingo list. What is this? Why does it matter? And who are the people who won the prize? I have a brief summary. The prize was awarded to John Clark, Michael Devoret, and John Martinez, and it's a case where much of it can be traced back to a single paper that was published in 1985. This paper shows results which demonstrate that macroscopic quantum tunneling is real. Quantum tunneling, you might have heard of, it's a case when a quantum particle can go through a barrier even though it doesn't have enough energy. That is, if the particle didn't have quantum properties, it'd be trapped. But if it has quantum properties, it can leak through the barrier. The probably best known application of quantum tunneling are electron tunneling microscopes. These probe basically the surface of a material atom by atom because electrons can tunnel into the tip of the microscope. However, this is a teeny tiny effect for single electrons. The three who won this year's Nobel Prize figured out that this can also happen for large collections of particles. In particular, they were looking at currents in superconducting wires. This is maybe not exactly your idea of macroscopic. Personally, when I hear macroscopic, I think of a bus. But a current in such a wire consists of millions of electrons, and that's quite large compared to the single electron level. What they showed is that the collective behavior of the current in the wire can tunnel across a barrier, so that's literally a gap. The wire needs to be superconducting for this to happen because otherwise the electrons don't behave as one quantum state. This means that these wires must be cooled to temperatures near absolute zero. You can see in this figure from the Nobel Prize winning paper that as the wire is being cooled, the current behaves in a way that it'd be impossible without quantum effects. The relevance of this effect, and this is why I guess they awarded it a Nobel Prize, is that it moved quantum physics into the microchip range. In the 40 years after their discovery, this insight exploded into a vast number of applications, the best known of which is probably quantum computing. Because once you have this current that can tunnel, you can also have a current that's both on and off. And that makes a qubit. Now, the quantum computers with superconducting circuits, which are being used by Google and IBM and Amazon and so on, don't use exactly the same technology they used in their 1985 experiment, but it goes back to what this group did in the 1980s. The fact is also being used in some experiments to look for dark matter particles that might interrupt the currents. Besides that, I don't think it has yet a lot of applications. I think that the biggest downstream effect of this discovery has been that it made quantum technology a reality. It's still mostly an academic enterprise, but one that's on the way to practical applications. And this has entirely changed physicists' attitude to quantum mechanics. In the 1980s, when these guys did their experiment, quantum physics was a mostly philosophical enterprise. No one thought it'd have much practical relevance one way or another. All this stuff with things being in two places and spooky action was just so far removed from anything tangible. But the macroscopic quantum tunneling was a major turning point that moved quantum physics into the tangible range, at least if you have a physics lab with superconducting wires. Back then, they argued all night over the interpretation of quantum mechanics. Now, they argue all night over the interpretation of quantum mechanics, but in a clean room. So, what are we to make of this year's Nobel Prize? It makes sense that rather than giving a Nobel Prize to quantum computing, they would give a Nobel Prize to the technology that made the first quantum computers possible. Though, as a theoretical physicist, I find it to be somewhat depressing. I, as many others, thought that the Nobel Prize would go to the theoretical work on quantum computing, to David Deutsch and maybe Peter Shor. It's tough to be a theorist. Then again, we must keep in mind that the Nobel Prize is not a community award. It's given out by the Royal Swedish Academy of Sciences, which is tasked with interpreting and fulfilling the will of Alfred Nobel. It's not great that this one person or the committee that selects the prize recipients should have such a huge influence on science overall. Then again, I think of Nobel Prize Week as Science Celebration Week. It's the one week of the year when the entire world wakes up and remembers how much we owe to science. And the one week my inbox tunnels through the spam filter. One of the most provocative new ideas I've seen in the foundations of physics in the past 20 years or so is that gravity is not a fundamental interaction, but instead caused by the increase of entropy. It's called entropic gravity. But entropy of what? Well, today I have an interesting new paper that offers a possible answer and that might actually move the field forward. Let's have a look. That gravity is really caused by entropy sounds crazy at first, but the more you learn about gravity, the more plausible it becomes. Black holes, for example, can famously be described as thermodynamical objects with entropy and temperature. This is very perplexing because entropy and temperature really aren't quantities you expect to appear in Einstein's theory of general relativity, which is all about space-time and curvature and so on. Then in the 1990s, Ted Jacobson pointed out that there are more general circumstances, not just black holes, in which one can reformulate Einstein's equations as being laws of thermodynamics with entropy and pressure and so on. Fast forward 10 years and we have Erik Verlinde, who derives Newton's laws from thermodynamics. Again, not full general relativity, but gradually getting closer. The analogy that Verlinde likes to use is that of some sort of materials made of long polymers that, if you warm them up, will contract, so they create an attractive force of sorts. Verlinde was very much inspired by shrinking sweaters, string theory, but he never really explained just what is supposedly going on for gravity. The problem is, if you talk about entropy, you have to talk about entropy of something. In a gas, for example, it's the entropy of the motion of the gas molecules. We could also talk about the entropy of, say, chemical reactions in combustion engines or magnetic moments, but the entropy of what is causing gravity. The authors of the new paper now have come up with a concrete answer. They say, suppose that space is occupied by quantum bits with a spin, so lots of little arrows. We've talked about this idea a few times previously. It's the It from Qubit program, that everything cheesecake is somehow a quantum computer. If cheesecake was a quantum computer, that'd explain why it disappears so quickly when observed. Hang on while I submit to nature. But to come back to gravity and the quantum bits, they now say that if a mass sits in this qubit environment, then that'll slightly align the directions of the spins. You see this in this image. Why? Well, that's the assumption that they make. If the spins are aligned, they are more ordered, so there is lower entropy around the mass. But the thing is now that if you bring two masses together, then the total volume in which the spins are aligned decreases. This means that the total entropy increases. So entropy increase will attract masses to each other. Then they show that this gives Newton's law. We talked about a similar idea a few months back, but there the maths didn't pan out. In this case, I think the maths is actually correct. The authors also say that if this idea is true, it makes some experimental predictions. Most notably, if what they say is correct, then gravity doesn't have quantum properties itself. Even if it comes about from qubits, it's an average, a bulk effect. This means that the experiments looking for effects of quantum gravity could rule it out. They also say that this environment of qubits would lead to decoherence where we don't expect it. That said, I think one should understand their proposal as what physicists call a toy model, and what in the startup business goes as as proof of principle. This idea doesn't have all the symmetries that are required to recover Einstein's theory, so we know that it can't be correct. This is why I give this an 8 out of 10 on the bullshit meter. But it's a starting point that might have potential, and I'm curious to see if it's possible to further develop the idea. Most physicists seem to be very convinced that gravity is a quantum interaction similar to the other interactions in the standard model of particle physics. Its mediator particle is the hypothetical graviton. I've always found it rather perplexing that they are so sure about this. Personally, I'm undecided on the question of whether gravity is fundamental or emergent from something else. I really think the jury's still out on this one, and each side has good arguments. And if gravity really comes from entropy, then my office is basically a black hole in the making. Mathematics as a field of research is being hard hit by artificial intelligence. This is only the beginning, but it's foreseeable that this'll get much worse. Much like calculators, the devices have replaced human calculators. Theorem-proving machines will soon replace much of mathematics. Not all of it, but much of it. That's what I think in any case. Mathematicians are currently somewhat in denial about this. Let's have a look. Earlier this year, both Google DeepMind and OpenAI reported gold medal level performance on this year's mathematics Olympiad problems. What's noteworthy here is not so much that they outperformed most humans' math skills, but that they did it using general-purpose reasoning models, not specially trained ones. This took most people by surprise. But mathematicians are not impressed, as Scientific American reports. These questions don't compare to the kinds of questions professional mathematicians try to answer, wrote Emily Rio, a mathematician at Johns Hopkins University. Field medalist Terence Tao argues that the comparison is unfair because AI has a speed advantage and generates possible proofs more like an entire group of people. Yes, so what? It's also unfair to compare a human to a calculator. That hasn't stopped tech from taking over the profession. DeepMind also just had everyone getting upset by announcing they have a method to find singularities in classic fluid equations. This sounds very much like they're after solving the millennium problem. That's about whether the Navier-Stokes equation can develop singularities. They did, in this case, not use the Navier-Stokes equation and instead worked with other fluid equations in 2 dimensions. But come on, we all know what's going on here. Demis Hassab is gearing up to become the first person to win both a Nobel Prize and a Fields Medal. Some mathematicians are fully leaning into it and work on automatic theorem proving. This isn't a new thing per se, but AI is certainly pushing this to a totally new level. If you need any indication that this is serious indeed, the NSF has a grant program to support AI-supported maths discoveries, and some private foundations have chimed in as well. On the flip side, I've also seen reports that AI-generated maths papers are beginning to pollute the archive. It's hard to know exactly, but in one particularly obvious case, an error rate became a blunder rate, and if that didn't make you laugh, the author is an expert in AI at Google. Mathematicians have reacted to AI taking over their field mostly by pointing out that they're irreplaceable. Community forums like Math Overflow and Stack Overflow discourage or just forbid AI-generated answers. They point out, quite correctly, that the currently used models, large language models, don't actually know what is or isn't a logically correct argument. But logic follows very clear patterns, and if the waters aren't muddied by spoken language, these systems can pick out the patterns. I think this is what we're seeing. LLMs become good at maths because if you think of it as a language, it's as unambiguous as it goes for languages, right after code. And most proofs follow certain rules. Again, LLMs can learn those. However, they don't have any way to tell whether a statement is true or false, like, for example, some math software can, at least not yet. In a preprint which just appeared 2 weeks ago, a mathematician raised two other relevant points. One is that an LLM will answer a question even if it's ill-posed. It'll not flag that actually the way you formulated the question, it might not have an answer. The other issue is that LLMs might not be able to explain what they're doing in a way that a human can comprehend. The mathematician Daniel Litt has likewise said that for him maths is all about understanding, and what good is an AI proof if the human doesn't understand it? From a purely utilitarian perspective, one could say, who cares? A proof is a proof, and most people already don't understand most maths proofs one way or another, so what's new? Then again, mathematics has never been a utilitarian enterprise. I think of maths more as a mix of sport and art. It's not really about the result. It's about how you do it. People solve maths puzzles voluntarily. They just enjoy mathematics, and I understand where they're coming from. Mathematics is the only place where we can find statements that are eternally, universally true. This is why I think it's extremely unlikely mathematics as a discipline will entirely disappear. However, most mathematicians will probably soon outsource most of their work to AI and then sift through the results. In some sense, this will move mathematics closer to being an empirical discipline. They'll be studying what AI can do. Andrew Grenville, a mathematician at the University of Montreal, explained in a recent interview with Quantum magazine just why this is so hard to accept. He said, wait for it, we'd be more like physicists. Oh dear. I think we need to update the 5 stages of grief: denial, anger, bargaining, depression, and fine, let the bot do it. My face has 2 settings: skeptical and very skeptical. Today I'm very skeptical about what's going on in nuclear fusion, which is more than you'd think. Let's have a look. The American company Commonwealth Fusion Systems just reported that they sold more than $1 billion worth of power from their first fusion reactor to the Italian energy company Eni. Interesting, because they don't actually have that reactor. The US Energy Secretary Chris Wright has repeatedly said that he believes nuclear fusion power is just about 5 years away. He recently told the BBC, for example, with artificial intelligence and what's going on at the national labs and private companies in the United States, we'll have that approach about how to harness fusion energy multiple ways within the next 5 years. And the technology, it'll be on the electric grid, in 8 to 15 years. Interesting, because the technology doesn't really exist yet. The American nuclear fusion company Helion, which is backed among others by Microsoft and Sam Altman, has begun construction on a nuclear fusion power plant in Washington. Helion uses an approach to fusion different from all other companies. It's basically a mix of magnetic confinement and inertial confinement that works by shooting fuel beams at each other and then squeezing them in a magnetic field. As a recovering particle physicist, I'd say it's basically a particle collider, and particle colliders are not known for being energy efficient. Still, by 2028, they want to deliver up to 50 megawatts of power to a Microsoft data center. Remarkable, because so far we haven't seen any evidence that they reliably achieve fusion to begin with, not to mention a net gain. In June, the British government put more than $3 billion into a tokamak, and if you need any indication that things are serious indeed, even the Germans have woken up. After the startup Proxima Fusion that wants to build a stellarator, the startup Marvel Fusion has raised more than $380 million to build a laser-ignited fusion plant in Germany. I think what's going on here is that despite all the warnings that nuclear fusion won't save us from climate change, politicians do use it as a promise of a big, bold miracle cure. It's a double excuse for using all that energy for AI. For one thing, we need AI to help us develop the technology for nuclear fusion, and then it'll make all that energy clean. It's a great plan. How can you not believe it? In other news, the British company First Light Fusion has changed course. If you remember, those are the ones with the big friendly gun that was shooting solid projectiles at a fuel pellet. That way, they wanted to deliver power to the grid in the early 2030s. They've now published a plan for a new nuclear fusion concept called FLARE. It's a two-step approach to inertial confinement. First, they want to squeeze the fuel slowly with an electrical pulse, then ignite it quickly with a small burst, for example, a short laser pulse. All this happens in a big pool of liquid lithium that soaks up heat, generates power, and also breathes tritium as a new fuel. Gun is the big friendly gun. They say the gain, meaning energy out from fusion divided by energy delivered to the fuel, could reach a stunning 200 to 1000. About the timeline, they vaguely say they hope to have a commercial demonstration potentially by the mid-2030s. Don't get me wrong, I've zero problem with companies changing course or updating plans. I just wish they'd be more transparent about it. It's hugely time-consuming to have to dig around in the internet archives. What are we to make of all this? I'm personally convinced that nuclear fusion is the power source of the future, and no, it will not forever remain a future tale. However, I haven't seen signs that any of these companies is anywhere near break-even. What I think will happen in the next 5 years is therefore that most of these companies will go bust because they've burned through all their money with not much to show for. The fun is in figuring out which ones that'll be. Personally, I think the most promising approaches at the moment are stellarators and, yes, laser-ignited fusion. Did anyone even notice that the NIF reported yet another record shot? This time they got more than 4 times the energy out of the pellet than what went in. And that's maybe a good way to measure progress, how headlines start falling flat. The James Webb Space Telescope has seen signals that move faster than light. It's true, but it doesn't mean that the speed of light limit was broken. Today I want to have a look at how apparent faster-than-light signals can be used in astrophysics to understand what happens in galaxies, but also at why some physicists, me included, think that faster-than-light signals might be real. This is what the James Webb Space Telescope has seen. It's ripples around the supernova remnant Cassiopeia A that seem to travel across space faster than light, or superluminal as physicists say. And while these ripples really do move faster than light, that's not in conflict with Einstein's theories. It's what's called a light echo. To see how this works, let me draw you a simple example. We have a supernova going off, and from the supernova there's a burst of light moving outwards in a sphere. Of course, reality is a little more complicated, but this is basically the spherical cow of astrophysics. This sphere of light moves, would you know it, at the speed of light. Okay, but now imagine that behind the supernova there is a cloud of dust, and let's assume it's basically a flat plane. When the sphere of light hits the dust, that creates a reflection, which we see. We then have to ask, what's the speed of the ring where the surface of the light sphere intersects the dust? And this speed turns out to depend on the angle at the intersection. At first contact, this angle is 0 and the outward speed is actually infinite. So we see a ring racing outward at faster than the speed of light, which then slows down. This is why a light echo can be faster than light. It's not that the dust moves faster than light, and it's not that the light moves faster than light. It's that the intersection between light and the dust changes faster than light. And this is what we see. The cool thing about this is that this apparent superluminal signal sweeps across the surface of the dust very quickly. So it's a great way to create a tomographic map that tells you what the structures are. And this hasn't been the only recent superluminal observation in astrophysics. Near the center of our galaxy, astronomers have tracked X-ray echoes from outbursts of the Milky Way's central black hole. And in the galaxy galaxy Centaurus A, astronomers have seen a blob of matter emitted by a black hole jet that moves at 2.7 times the speed of light. Okay, but now for the question everyone's actually here for. Could faster than light ever be real in the sense of carrying information faster than light? Physics does have a few doors for this that are open, at least mathematically. We put a do not enter sign on them, and then we peak. One intriguing example is the reason why quantum mechanics doesn't allow information to travel faster than light. It totally depends on the probabilistic interpretation of quantum physics. Indeed, you can prove that if there is any tiny deviation from these probabilistic predictions, then you could use that to send information faster than light. Now, almost all physicists take this to mean that nature is fundamentally random in the quantum sense, and this is what protects the speed of light limit. The only exception that I know of is Anthony Valentini, who thinks that the quantum randomness that we observe is a good approximation, but not always correct. And this means that there are cases when information can travel faster than light. It's a totally underexplored argument, I think. Faster than light motion also appears in many attempts to modify gravity. That includes approaches to describe dark matter. I've toyed with these theories myself, and basically whatever you try, you always end up with some superluminal propagation. Now again, most physicists take this to mean that something's wrong with these theories, but I wonder, maybe the mathematics is trying to tell us instead that we should seriously consider faster-than-light motion. And then there is Einstein's theory of general relativity itself that allows certain types of travel faster than light. For one thing, it allows wormholes as shortcuts. You don't actually travel faster than light through the wormhole. However, you'll be faster than light that didn't go through the wormhole. Warp metrics exploit another peculiar feature of general relativity, which is that while you can't move in space-time faster than light, space-time itself can move faster than light. Physicists believe that this actually happened in the early universe, that space expanded faster than light. So mathematically, you can make warp drives work. So far, however, we don't know how to create and maintain either wormholes or warp metrics, as these seem to require negative energy, which for the time being is all being used up on Twitter. Thanks for watching. See you tomorrow.